Evolution of a nervous system. Certain fundamental principles are always found underlying the essential phenomena of life, which, first recognizable in the most primitive, prove afterwards to be just as operative in the most developed forms. The greatest growth, for example, in either the vegetable or animal kingdoms, a towering oak or an immense whale, have to begin like every other living thing as veritable microbes in a single microscopic cell. The inner structure of that cell itself has certain invariable elements which are equally present in the first vegetable and in the first animal cell. Thus, every species of plant or animal contains in its first cell a fixed, specific, and always even number of bodies called chromosomes, because they can take a dye, and this number regularly recurs in all the subsequent cells of.
To listen to the complete audiobook for free, check Amazon Audible. Link can be found in the description or the first comment.
Cells of the future body, though they be millions. Thus, in the cells of the mouse, the salamander, the trout, and the lily, the chromosomes always number 24. In the ox, the guinea pig, in man, and in the onion, the chromosomes always number 16. In the shark, the number is 36. In the grasshopper, 12, and so on. It is from such facts, and others like them, that the eminent naturalist von Nageli was led to say that all life is one. But nowhere is the steady sway of fundamental principles so illustrated as in the development of a nervous system. From the first beginnings of the nervous system in a polyp up to the marvelous brain of man, certain primary laws are always operative, without their ever being afterwards repealed or superseded. If, therefore, we are to understand the complex, we must first study the simplest organization, while assured that what is illustrated by it will continue recognizable in every further development, however great or manifold. In studying the development of a nervous system from a physiological point of view, the first principle discernible as governing that development is what in any other connection we would term discipline, and we cannot do better than to note how the conceptions suggested by that word are applicable to our subject. One of the definitions given in Webster of the word discipline is subjection to rule, submission to order and control by severe systematic training. The central idea conveyed by this definition is that discipline in no way represses activity, but directs it by means of regulated restraint. Without activity, there could be no discipline, for there would be nothing then to discipline. The word, therefore, implies some kind of energy made to subserve some purpose which it would not effect unless it be put under control. But in its usual and most correct sense, discipline is not a word which can be applied to an inanimate force. It is an exclusively nervous system word. You cannot properly say that you will discipline your watch if it goes too fast, though you can say that you will regulate it. Nor can you properly say that you have disciplined the energy of steam when you have made it subserve your purpose by putting it under control in an engine. It must always be something nervous that is disciplined, so that even in the bodies of the highest animals, nothing but that which is nervous can be either disciplined or trained. This may seem a singular statement to some, as they think of the highly trained muscles of the legs of a dancer or the fingers of a pianist. But it is not the muscles in these cases, but the motor nerves of the muscles, which have been so wonderfully disciplined. For neither of these instances of supposed muscle training can be compared for complexity and difficulty with the training of the muscular organ, the tongue, for the movements necessary for articulate speech. An animated orator has to make a greater number of rapidly succeeding and yet perfectly adjusted contractions and relaxations of his muscles of articulation than any famous performer on a musical instrument. But how shall we explain the authenticated case of a man who could speak English, French, and German, and who suddenly became unable from an attack of right hemiplegia or paralysis on the right side of his body to make his tongue work out a word in any one of the three languages. What was the matter with his tongue? Nothing as a muscle or muscular organ. In fact, it could not work as well as ever in assisting mastication and swallowing. Why, therefore, could it not talk? Solely because its nervous direction for the movement in speaking was lost, while its nervous direction for the movement of mastication was retained. But if its pair of hypoglossal nerves were also cut, just as the accident which has cut his hemiplegia had severed the connection with the higher brain centers, then the tongue would have failed equally to assist in mastication and in deglutition. It is a mistake, therefore, to say that muscles, as such, can be taught to do anything. Nothing can be taught except that which is nervous. This principle is far-reaching because, among other things, it introduces us to a second element of fundamental importance and which is characteristic of the nervous system alone, namely, that of graduation of rank in work or function. Every tissue of the body, except the nervous tissue, has but one dead level of function. No one bone or bone cell has any higher rank than any bone or bone cell, any more than one brick in a building is of a higher or more important grade than another brick, simply because it is put above or below. And so muscles are little else than duplicates of each other in function, because wherever they are, they will be found to do but one thing, namely contract and relax, and nothing more. There is therefore no such thing in the muscles as one set governing another set by virtue of poor innate superiority, as the rider is superior to his horse. The horse might claim against his rider the greater importance because he does all the going, and so he might if he were like his rider and not a broken-in horse. But just this difference meets us in the case of the gray motor cells of the spinal cord and the gray motor cells of the surface of the brain. The gray motor cells of the cord do all the going of the body, for even the so-called cranial motor nerves really belong to its system. Not a muscle of the body is directly under the control of those aristocratic motor cells in the topmost layer of the brain. The cord might say to the brain, "If you wish to move hand or foot, you have to ask me to do it for you." "Very well then, do it," is the brain's answer. "But don't you move hand or foot till I tell you, for since I have been evoluted up here, you have lost your senseless independence and must obey me." You were the original nervous system, to be sure, just as there were horses before there were men to ride them. But since I have come, I am above and you are below, and as it is, it took me long patient training and a great deal of trouble to break you into my service, so that you would act according to my orders. Rank, however, always implies an ultimate below, from which everything starts as a common foundation for all subsequent gradations. And so we will begin now with the simplest illustration of what a nervous system is. Reduced to its most primitive form, as it is in the lowest animals which show a trace of nervous system, it is proved to consist of three parts. 1. A nerve filament which receives and transmits a stimulus to 2. A nerve center of soft gray cells and fibers which receive this stimulus and which center reacts to this stimulus, never on the nerve which brought it, but on 3. A nerve filament which proceeds from the center. Hence, these two filaments are accordingly named: the first, afferent, because it transmits to, and the second, efferent, because it transmits from the center some nervous vibration. One of the commonest examples of efferent excitation is when muscles contract in response to the efferent excitation of their motor nerves. A fair illustration of this mechanism can be found in ourselves in the act of winking. You can abolish the power to wink in one of three ways. You may do it, first, by cutting the branch of the fifth cranial nerve, which transmits sensation to the nerve center for winking at the top of the spinal cord. This center then does not know that any winking ought to be done because it depends for all news of that kind on the sensory fifth nerve, and that has been cut. Or you may abolish winking by cutting the proper branch of the seventh pair of cranial nerves. Then no matter how the fifth nerve tells the center that it how to wink hard, the center answers, I cannot do it, because the seventh nerve, which is the efferent or motor nerve that works the muscle of the eyelids, is cut. Or, lastly, with both the fifth and seventh nerves intact, no winking will occur because the nerve center itself has been deadened by some narcotic poison. From that simple beginning of a real nervous system, one can proceed step by step with animals still utterly brainless, but which have developed a complicated nervous system, and yet in them no other mode of working than by afferent, centric, and efferent elements can be discovered. What one finds in these small organized nervous systems is a greater number of these centers, each with its afferent and efferent nerves, but with one important addition, namely, that the separate nerve centers in them are connected by short nerve fibers, which are for the purpose of enabling the centers to work together. Something as the jars of a laden battery are connected by short chains. A still further development shows a regular chain of such nerve centers forming a distinctly ascending series, whose functions never change or abolish the original afferent and efferent mode of working, but instead show a more and more perfect harmony of action between the several parts. By this harmony of action, new results in movement, or in the direction of movement, are secured, which would be impracticable were the separate centers to work independently. After a certain number of nerve centers have become associated, according to the scale of the animal's development, we find that the mutual cooperation of the centers begin to be plainly more frequent in certain directions than in others. That is, that it seems easier for the centers to act together to execute some movements than to execute other movements. When we examine why this is so, it proves to be because of the more frequent repetition of certain afferent stimuli than of the other afferent stimuli. Repeat one afferent excitation 100 times and another only once, and the movements consequent on the first are clearly much more readily caused than those following on the unusual excitation. Therefore, we have come now to the second and most important principle of all, in the organization of a nervous system, and which we have alluded to in the previous chapter, namely habits. The whole nervous system, indeed in any animal, man included, is first organized by habits. However complex, for example, be the movements executed by muscles in order to produce a given effect, e.g., the movement of the eyeballs, some muscles contracting strongly, others most gently, others again relaxing just enough to allow their opponent to contract just so much and no more. All these perfectly associated movements are nevertheless explicable only as the slowly acquired habits of the centers which supply those muscles with their motor nerves. Hence the important question, how did the centers come to acquire these habits? The answer is, from 1,000 times repeated afferent impressions along the optic, or sense of sight nerve, is habituating the efferent or motor nerves of the eye muscles to act together. Physiologists, therefore, when they speak of nerve centers being organized to perform such and such functions, mean not that the nerve centers have been created so from the beginning, but that habits has so organized them. But the important principle to bear in mind here is that it is the afferent segment of the nervous system, or that which is acted upon by stimuli from the outside world, which is the ultimate source of this great fashioner of the nervous system, habit, and not the nerve center itself, nor the efferent segment. This principle well nigh overshadows all others in its bearing upon the question of the origin and development of a nervous mechanism. We will gain no insight into the deeper problems of nervous organization if we relax our hold on the continuous presence and operation of afferent excitation all the way from the swaying arms of a hydra fusca up to the successive trains of thoughts in a human brain. We thus speak of it now because further on we will have to refer repeatedly to the place of the afferent in discussing some subject. Second to none in importance about our own mental operations. Here, however, we start with the fact that it is the afferent only which connects with the environment. Upon the afferent, the nerve center wholly depends, not only for the primary source of its activity, but for the organization of that activity so that it can ever become uniform. The reaction of a nerve center to an afferent stimulus has been likened to an explosion of energy set free by the lighted fuse of the afferent. But that explosion would be an explosion and nothing more, but for that one great fact about the afferent nerve itself, namely that it always causes the explosion to be in one direction only. Over and over again, it does exactly the same thing as at first, and thus trains the nerve center to react only in one fashion. All this is due to the great law that an afferent nerve never varies in what it does. As Professor Sherrington expresses it, the afferent nerve, extending from the receptive surface to the central nervous organ, forms the sole avenue which impulses generated at its receptive points can use. It constitutes a private path, exclusive to the impulses generated at its own receptive point, and other receptive points than its own cannot receive it. The nerve centers, therefore, become accustomed to react in the same way to afferent stimuli, because these stimuli are never mixed or confused with others. Presidential Address, Section of Physiology, Brit Associate Science, 1904. It is quite otherwise with either a single efferent nerve or with any organized nervous path for efferent impulses, for any single one of these may be used in response to a great variety of afferent stimuli. Thus, the act of coughing is executed by a whole group of motor nerves acting together in a regular way. But this same efferent path for coughing may be used by a number of very different efferent stimuli, starting from the nose, pharynx, larynx, bronchi, pleura, stomach, brain, or other organs, so that not uncommonly it requires some search to find what the particular cause of the cough is. It may be a pain in a child's ear, or a worm in the intestine. An afferent stimulus, on the other hand, never breaks its rule of using none but its own path of excitation, and hence it is the source of sources of this great factor, habits, in nervous evolution. Another peculiarity of afferent excitation, to which we shall have to allude again in the very highest connection, namely in the succession of ideas in human thinking, is that an afferent stimulus, though always itself single, once it excites an efferent act in a nerve center, may have that excitation spread from center to center, as it were, like so many successive efferent explosions. Thus, a sneeze is always due to the excitation of a minute twig in the sensory or afferent nerve of the nostril, which then transmits it to an efferent center in the medulla oblongata at the top of the spinal cord. This efferent center then sends this excitation to 55 pairs of efferent centers to cause them to call their 110 muscles into one combined and well-regulated sneeze performance. A number of writers on nervous disorders seem to regard an attack of epilepsy as due to a spontaneous discharge of nervous energy in some cortical brain centers, the motor area being especially involved when the attack is accompanied by convulsions. As no other examples of spontaneous efferent actions can be cited, but on the contrary, such always follow upon a preceding afferent stimulus, I would ascribe the true beginning of an epileptic paroxysm, whatever its form, to an abnormal afferent excitation. This view of the nature of this serious nervous disease has an important bearing upon its treatment, as I explained in an article on the pathology and treatment of epilepsy in the NY Med Journal, November 8 and 15, 1902. All that we have said therefore finds a complete illustration in the structure and functions of the spinal cord in all vertebrates. The spinal cord, which is the original nervous system in every vertebrate, as it is the first to appear in its embryonic development, consists of a great number of nerve centers, one above the other, all receiving their efferent and giving off their efferent nerves on each side, and as constantly joined together by tract of communicating fibers, until finally the whole muscular system of the body is found to be under its exclusive control. As remarked before, no primary law of function in the nervous system is ever superseded by any later development, and so, however great to be the additions afterwards of brain centers or functions, yet the spinal nerve centers retain all their original prerogatives, quite as much in man as in any of the rest of the animal world. If, as remarked above, you wish to show the cunning of your right hand in any work of skill, or the fluency of your speech with your tongue, your designing and talking brain has to ask the spinal nerve centers for the muscles of the hand and for those of the tongue to direct those muscles to do the work for it. Meanwhile, this wonderfully organizing power of efferent habit works out results in creating special functions or modes of working in the spinal cord, which actually startle us with their close resemblance to what we are accustomed to regard as manifestations of design or purpose. Thus, if a vigorous frog be suddenly decapitated with a sharp knife, and its headless body be put on a plate, it will forthwith jump up and assume on the plate a perfectly natural, if not somewhat impertinent attitude. If now a small drop of acetic acid is applied on the frog's side, as soon as it begins to irritate the skin, the headless frog gravely and deliberately raises his hind leg and brings up his foot to scratch off the acid. If more acid be applied, it brings down the arm to up-scratch the same spot. And if the irritation continues, it begins to lose balance by trying to bring up the other leg also, until at last, as if the itching had become intolerable, it makes a most natural dive for the floor. An amusing illustration of this kind once occurred to me in my college days, while fishing in a western stream with a classmate. My companion's luck had been poor, when at a deep, promising pool he became greatly excited by a powerful bite, with a pull which bent his pole near double, only to find out at last that it was drawing up a great mud turtle, which had swallowed the hook beyond mistake. In vain my friend tried to persuade the turtle, when he landed him to put his head out from under his shell till he could get the hook free. Finally, as he had no other hook, my friend hung the turtle over a branch and sawed his head off with his jackknife. Down at last dropped the turtle's headless body, when to our astonishment it straightway walked some 2 yards right into the water and dove off into the deep pool, just as if the creature kept an extra head under its shell to put on in an emergency. End of section 7. Recording by Thoria.
To listen to the complete audiobook for free, check Amazon Audible. Link can be found in the description or the first comment.